Good afternoon, everyone. Welcome to KubeCon Week. I'm really honored that you're here to join me on the first day to talk about a sort of funny, less cloud-native thing than you would normally think of, which is how do we secure cloud-native workloads starting from just a metal server. My name is Tyler Schade, and I am a software engineer at GEICO Insurance. I lead GEICO's hybrid cloud engineering team, which focuses on building out common infrastructure service layers across multiple cloud providers and on-prem data centers. My teams work on building Kubernetes clusters, providing secure zero-trust application networking for workloads, and managing traffic for those workloads from the edge all the way across the various compute providers that we support. I'm not here to sell you anything today, but if you didn't know, 15 minutes could save you 15% on your car insurance. All right, cool. Now that I've gotten that out of the way, a little bit more about me. I joined GEICO 15 months ago. Before that, I had been working in various startups, building infrastructure and security systems. GEICO is in the middle of undergoing a really interesting digital transformation, starting with the foundational technology stack and moving up to the applications, where we want to be able to support modernizing, making our default settings more secure, and giving sort of a faster playground for developers working on applications to be able to innovate from. I had started my career about 10 years ago as a web developer, and slowly sort of got interested in moving further and further back across the stack, understanding what was going on, the layers underneath me, and so that led me to infrastructure and security about 5 years ago.
When I was a web developer, we deployed to some metal servers. We had some on-prem stuff, but it was very early on, and I wasn't involved in the infrastructure or management of it. And so I was really excited to join GEICO because GEICO was building data centers as part of this transformation. And I was like, well, this is gonna be really cool, right? There's nothing cooler than just a room full of racks of servers at my fingertips. This is gonna be really fun. And it was really, really interesting to step out of the garden, the curated garden of the public cloud, where there's a lot of things that just work, and step into a world where some of those things work in some places, because we still have the public cloud, but some of them don't work at all, and you need to figure out how to do them yourselves. And that was something that I knew in my head would be part of this journey, but I had no idea sort of how many places I was going to find something that I hadn't really thought about how to do from the ground up before. And this talk is the output of one of those explorations. So a quick outline of where we're going to go today. We are going to quickly get through some foundations about security and identity. We're going to talk a little bit about machine identity and why it's important to identify not just your workloads, but your machines themselves. We will briefly cover TPMs. We'll talk about SPIRE for 30 to 60 seconds. And then really what we're going to do is we're going to spend some time talking about how you can put these pieces together to use TPMs to actually attest your bare metal servers in a cloud native way. So one particularly thorny problem that I didn't have to think about ever, practically, in the cloud with cloud infrastructure was how do I bootstrap the initial trust root of an entire infrastructure system? Because the cloud provider does that for you in most cases. In a data center, you have quite literally, like I said earlier, a room full of racks of usually commodity servers, and you have a foundational network that's laid down, and then you need to go build those primitives on top of it. And I just hadn't really considered how to start from that place. And so what I'm going to show you today is one way to solve this problem, and to uniquely, securely prove the identity of each machine in your data center. This talk is an overview of one solution for the problem, but there is no one right way to solve this problem. There are a lot of wrong ways. We'll cover some of those. There are some ways to solve this problem that are going to be harder for you, but I want to be clear that this may or may not be the right way for you to solve the problem. Everyone has different constraints. I work in a regulated industry. You may not. If so, you may have more freedom to innovate or move rapidly. And at the end of the day, every security architecture, every security architect has to make a decision about foundationally what is in scope to be protecting against and what is not in scope to be protecting against, right? Otherwise, if we didn't make decisions about what was important and strategic for us to secure in our security architectures, we would all work in air-gapped bunkers underground with no internet. And then we wouldn't get anything done, but it would be highly unexploitable. So the other thing that I want to say before I get into the content is I am not a cryptographer, I am not a mathematician, and if you come up and ask me many detailed questions about the mathematics of a TPM, you and I are going to go to ChatGPT and the TPM spec together, and we're going to learn that. What I am is I'm an infrastructure engineer who had to use this to solve a problem. And if you are in the audience and you are a cryptographer, a mathematician, or you know more about TPMs, please come talk to me afterwards because I really want to geek out with you and ask you a bunch of questions that I haven't been able to figure out myself. Okay, with that, let's get started. So for security, for a security architecture, you have to decide, like I said earlier, what is in the scope of your architecture, what are you trying to protect against, what are you not trying to protect against. I will lay down sort of a foundational assumption that I make when I'm designing security systems, which is that the identity of a process, of a machine, or of a network request is always in scope for the architectures that I'm trying to build. So I take an identity-first approach to being able to secure a system. I want to be able to know what the things in this system are. I want to be able to know who they are, as in what they're acting as at that time. And I want to be able to understand that and verify that all the way up and down the stack. So to me, security requires strong identity. That's pretty tautological to me. I'm probably not going to spend a bunch of time for time's sake justifying that. The other thing that I fundamentally believe about building secure systems in 2025 with the advent of cloud, securing your perimeter is a great first step, but I think we would all agree, I hope we would all agree, it's very, very far from the last step. Right? If you have a hybrid cloud approach, if you have a multi-cloud approach, even if you have a self-service provisioning approach in the public cloud where many different people from around your company get to go create cloud resources, just setting a perimeter and saying this is our secure stuff and then everything else is untrusted and verified, but everything within this zone we just take for granted, that's probably not going to end in a very good place. And then the third thing that I would say that's sort of foundational here is that identity is a hard problem. There's a lot of different kinds of identity. It's hard to solve comprehensively. There's user identity, there's non-human identity. In 2025, there's AI agent identity, which is fun and not something we're going to talk about at all. There is machine identity, there's workload identity. It goes on and on and on and on and on. But identity systems usually start with authenticating a party as a well-known identity, and then using that identity to be able to entitle the party, to authorize the party to go on and to do something with the privileges that that identity entitles them to. And at some point along the chain of building an authorization or an identity framework, you have to start out by deciding what you're going to trust and what you're going to take as trusted, right? If you use an enterprise IDP for securing your user identity, you're delegating that root trust to somebody like Azure, right? If you're using Entra. If you're using Okta, right? That's very common in users to use a IDP to go build sort of a user identity chain. And a root for your trust in that process. This is a lot harder to do with machines, but there are some solutions for it. And so the ones that I used for the first, 6 years of my career in infrastructure were the cloud provider primitives. And they're really great. They all take a pretty common approach to being able to assign a unique identity to a unit of compute that they vend out to you. They are traditionally built around answering the who you are question via IMDS, which allows a process running on the machine to be able to hit a special network endpoint that tells it who it is. And then there's various forms about a signed document or signed token based off the cloud provider to be able to also get a token that signifies that this indeed is a verified machine, a credential from the cloud provider using their root of trust, if you will. So in AWS, this is the instance identity document. You can also delegate instance IAM roles to AWS machines. In Azure, there's something called Managed Service Identity. They also have an IMDS implementation for answering the who are you question. GCP, there's an instance identity token. But across the board, these are platform-specific primitives, right? So an EC2 instance identity document means nothing outside the context of AWS. You can validate it outside the context of AWS if you give your process permissions to call back into AWS to validate it. But you can't take an EC2 instance identity document and really do anything useful with it in Azure, for example. And you certainly can't do it on-prem. So when I had to go solve this problem about how to identify my machines, the tools that I was used to using, cloud provider, attested identity, just didn't exist. So there are some well-known approaches to being able to identify a machine on-prem, but you have to do it yourself or go pay somebody to do it for you. I like figuring problems out, so and I'm getting paid to solve this problem, so company already checked the first box. And some of the approaches that are pretty common are using a static credential, a token, to be able to allow a machine to attest its identity. This is effectively a password. This is probably the least ideal option out of all of them and something we really wouldn't want to do. Other less ideal forms of identity involve trying to use the network. So being able to use DHCP to be able to provision every machine with a host name that is strongly bound and restrict permissions for users using the machine so they cannot change the host name because host names are fundamentally changeable. Some people traditionally in a perimeter-based security model use IP address and IP network CIDR range, right, to be able to build out sort of subsections of networks that where machines have common privileges and they're not actually identifying the machine itself, but they're able to sort of use it to build a layered framework where they're able to at least identify like the network zone that that machine is associated with. And then there are some more secure approaches like using a SSH CA to provision every machine with a unique host key. And this is really interesting to me because I've never heard, well, I haven't heard of a lot of people doing this. Just like by a show of hands for your compute instances, does anybody actually run an internal SSH CA? One? That's exciting. That's cool. Okay, so yeah, it's not something that a lot of people tend to do. They tend to vend out, let the OpenSSH bootstrap process vend a host cert and then trust it, right? This is why when you go and SSH to a new server, you have to accept the key pair that you've never seen before, etc. Another common approach to doing this is put a unique X509 certificate on every machine and execute some sort of proof of possession challenge against that X509. The problem is, how do you get that X509 on all of your machines? The X509 is fundamentally exfiltratable. It's something that somebody can take from one machine and go put on another machine. So you have to be really careful about your permissions, making sure nobody takes it to a place it shouldn't go, etc. Then there's the TPM. And the TPM just works. If it's done properly. And there's a lot of nuance going into how that actually just works. But in the interest of time, I'm going to move along. The one point I did want to make about the SSHCA and the X509 proof of possession process for attesting a machine, it's not only can those credentials be moved, but they also require you to do something to the machine to get that credential on. As in, you cannot securely reuse the same credential. It must be a unique credential, which means you must provide it at post-provisioning of the OS. And as somebody who really likes to start up machines with everything they need, that was not something I was very interested in. So quick crash course on what the TPM is. The TPM is the Trusted Platform Module. It is a secure crypto processor implementing an ISO IEC standard, and it is actually present on most servers and most consumer computers. If you are running Windows 11 plus specifically, your laptop has a TPM on board. TPMs are probably all around us in this room right now. There are various forms that a TPM can take. There are physical chips, there are in-processor, in the CPU sort of software, firmware implementations. There are virtual TPMs, and then there's like fully emulated, fully software-backed TPMs. We're mostly gonna be talking about doing things with physical chips today because the rest of them are irrelevant, and an emulated TPM is very cool for testing, but not something that's a great security primitive at the metal level. TPMs can be used to perform a variety of different cryptographic functions. It has a hardware random number generator. They can do key generation, they can do key persistence, they can hash hardware and software configuration and state. It has a small chunk of persistent non-volatile memory that can persist key material or other secrets, for lack of a better term, across reboots. And then it has some volatile memory that'll be wiped between reboots that you can use sort of for a session, which is what using a TPM, opening and closing a socket to a TPM is called. It's called a session. There are a couple different versions of TPMs out in the world. There's TPM 1.2, there's TPM 2.0. Everything I'm going to talk about in this talk is TPM 2.0. If I just say TPM, it's TPM 2.0. I don't know much about TPM 1.2 because I started using TPMs with 2.0. So, TPMs, like I said earlier, store and can generate a number of different keys. There is a special key called the endorsement key, or EK, which is burned into non-volatile memory, so persistent memory on the TPM by the manufacturer. Every TPM that gets manufactured that is compliant with the TPM 2.0 standard gets a unique RSA key pair, usually an ECC key pair too, that is created by the manufacturer, signed by the manufacturer's root, and identifies each TPM device. So we have one sort of part here of what we fundamentally need to be able to prove identity, which is some unique credential. TPMs also store keys in a really interesting way. For asymmetric key pairs, the TPM stores both the public and the private key, but allows the public key to be read. The private key is stored in special memory that can never be read, but the user of the TPM or a process running on the machine can go ask the TPM to perform some cryptographic operation like encryption, decryption, signing with the private key, but the TPM is doing it for the user or the process. The key is never read from the TPM, the private key. This all takes place via a very fun and very hard to follow, very, very low level API. There are some great SDKs too that I've linked to in the end if you want to go read some more of the code to see how this works. But the second key that we really care about here is called the attestation identity key, AK or AIK, and this is a short-lived key associated with the EK via a wrapping process. Wrapping is one of those things that when I called out at the beginning that I'm not a cryptographer, I cannot fundamentally explain wrapping to you. It sounds to me like the closest thing I can think of is signing it with the EK, but it's considered a child key. It is not quite a signing operation. If you understand it, please come and talk to me because I'd like to learn more about it. But fundamentally, the AK can be used to prove that a given operation was actually performed by the TPM. So now we have a unique credential, and we also have a way to be able to prove that that unique credential was used to perform some operation via the AK. Now, this is cool. We've got a lot of keys. What do we do with all these keys? Okay. This is where SPIFFE and SPIRE come into the mix. If you haven't heard of SPIFFE and SPIRE, it is so out of scope for the amount of time that I have left. I wish I could go and tell you everything about it. Come find me later. I'm happy to give you a crash course. Very briefly, SPIFFE is a standard for being able to attest and issue workloads and machines identities. SPIRE is an open source CNCF project that implements the SPIFFE spec. SPIFFE is everywhere. It is supported by so much. Vault, Cert Manager, Istio, Envoy, many cloud native software supports some part of the SPIFFE spec. SPIRE sort of provides a reference implementation for all parts of the SPIFFE spec. The high level SPIFFE and SPIRE architecture is that you have a centralized server that stores a signing CA. And then you have run an agent on each node that is responsible for authenticating and attesting the identity of the node to the server in exchange for a certificate. It takes an attestation-based approach to identity, which combined with the TPM allows us to be able to go bootstrap our root of trust for what a machine is. SPIRE specifically supports a really rich plugin architecture too. We're going to be talking about that in a little bit if I don't run out of time, and allows the user to be able to create their own attestation methods. So yeah, there is a out-of-tree plugin. So it is part of the SPIFFE org. It is not part of the SPIRE project itself. There is a SPIRE project itself that supports a different kind of TPM attestation called device ID. Device ID unfortunately requires post-provisioning out-of-band operations to be taken to allow it to happen, which per the requirements I laid out earlier, I really don't like to do because I like to boot up my machines and have them ready to go. There is a node attester, which is responsible for actually attesting and interacting with the TPM on a given machine. And then there is a SPIRE server node attester plugin as well that is responsible for checking an allow list of TPM EK public hashes to be able to go and prove that a machine is not only that a given request, attestation request, is not only from a specific TPM, but that it's from a well-known TPM. So it's effectively acting like a registry. The core concept of what we're trying to get to with TPM attestation is leveraging that unique EK in the TPM to prove that the connection is actually coming from a given machine. The flow usually works like this. The agent generates an attestation key and then sends the attestation key, public key, and the EK public key to the server. The server is going to check the EK and compare it to that allow list, which in this plugin is implemented as a static file that is read on every attestation request. So you can go update the file, you can store it in Kubernetes as a config map and mount it in. There's various ways to operationalize this. Once the server validates that the EK is actually a known EK, it then it produces a challenge for the TPM to complete, which is essentially sending it's called a credential activation challenge, which is a special TPM protocol message requesting the TPM to validate the parameters of an AK and certify that the EK is present on the TPM by including a secret that can be decrypted with the private key of the EK. So it signs it with the public key that was presented to it, and then the TPM does some fun stuff with the AK and the EK to be able to actually get the value out, at which point the agent sends it back to the server. The server compares it to the secret value that it generated, and if all has succeeded, now we've uniquely identified this machine. That is quite a mouthful, and so with the time I have left, I am going to show you a little illustration I put together of how this works. The first thing that happens at position 1 is the SPIRE agent starts up and connects to our SPIRE server. The next thing that happens is the SPIRE server sees a new connection and initializes the agent attestation flow. At this point, if you're using the SPIRE TPM plugin, if you're trying to attest your identity via TPM, the SPIRE agent itself is going to immediately delegate the attestation to the TPM plugin, which is going to go ahead and open a session for the TPM device. We're going to skip a few steps. The TPM plugin fetches EKs from the server, from the TPM. The TPM can have multiple EKs. Takes the first one in the list and uses that to generate a new AK. Then sends that to the server. This is where the server performs the check to ensure that the EK is known by hashing that public key and comparing it to its list of hashes. Then it sends the credential activation challenge encrypted with the EK to prove the validity and the residence of the AK. The SPIRE TPM plugin sends it back over the same session to the TPM and says, would you please validate and decrypt the secret value? If all goes well, the TPM activates. The credential activation is like a TPM specific term, but it activates the attestation key, it sends back a decrypted challenge, and the plugin then forwards that response to the server. The server makes sure it was the secret that it sent originally and provides an identity. That is the flow. I wish we had more time to walk through it in detail, but 25 minutes is 25 minutes. So very briefly, just to wrap up, I've got some ways I think that the community can improve this, some things I want to build to help make this easier. I'm particularly interested in being able to attest values from the TPM called PCRs, so that tie into the boot process to ensure that the configuration of a specific server is consistent. I think it's a real gap right now. But that said, if this was interesting to you, I am hiring. We have a bunch of open headcount for people, so we are looking to add to the team. If you want to come work on these challenges, if you, like me, are also excited about the possibility of going into a data center full of servers that you and only you control, well, you and your team control, let me know, and I'd love to tell you more about what we're doing and see if there's a fit. So these are some resources to learn more about everything that I talked in here. There's this great book that's available for free called A Practical Guide to TPM 2.0. It is very dense, but it's a very fun read. And then I have a bunch of code references that help you actually walk through logically what's happening. And if you like to read Go, allow you to go all the way down to the actual TPM operations themselves. So that is it. Thank you for coming to my talk. I don't know if we have time for questions. If we do, please feel free to ask any questions as long as they don't involve credential wrapping. Thank you. Pardon?
What OS are you using?
At work or in my life?
Oh, no, for this implementation.
Oh. We run right now Ubuntu 24. We are building our own curated, hardened, not a distro, but sort of slimmed down version of Ubuntu with our own package set. So yeah, it's all Ubuntu based. Yes.
Have you guys considered, like, isn't even a thing or useful for like a TPM pass-through to VMs, or any thoughts about like either of those?
Yes, we have talked about this a lot. We have a virtualization layer that I could talk for a while about how our data centers work. We run one big Kubernetes cluster in the data center and a couple small ones. Then we have a virtualization layer that we build on top of that. We also run some containers on the metal. It would be really nice to be able to pass the underlying host TPM to the VM. But one of the reasons we use VMs is for things we want to be able to live migrate. You cannot live migrate a TPM because you're going to lose the identity. So that is a challenge. We had looked at vTPMs for that, but we use OpenStack to run our virtualization layer. And very similar to whether you love OpenStack or you don't love OpenStack, I know it's mixed feelings. I have my own set of mixed feelings. One of the things OpenStack does give you is they give you instance metadata like you get in the public cloud, right? So you can leverage that to do your VM attestation at a hypervisor level.